then let's finish up momentum with something called the law of conservation of momentum. So find me this page if you haven't already. I need time for coffee. He's out of here. Okay. Oh. Okay. Here we go. So, law of conservation of momentum. There's a few things in physics that are conserved, and you've talked about energy conservation before. And you talk about it in chemistry. You talk about it in physics in grade 10. The idea that like you can't, energy's not created or destroyed. It's just moved around. And if you take a look at your system, if you make the system big enough, the energy is always going to be accounted for. You don't have the energy you need, so you go buy a sandwich. You eat the sandwich, your body turns the contents of the sandwich into energy for you. But if we look at the system large enough, then no energy's been created. It's just been moved from, again, whatever you want on your sandwich, but it's been moved from those things into you. But how did it get into the sandwich? Well, if you're a vegetarian, there's energy that went into growing of the veggies. If you're a carnivore, there's energy that went into the growing of the veggies that the cow or the pig then ate, that went into the bacon and ham on your sandwich, whatever it is on your sandwich. Like, it's a constant movement rather than a creation or a destruction. Momentum is the same, believe it or not. The law of conservation of momentum says that when you're looking at a system, momentum's always got to be conserved. For every action force, there is an equal and opposite reaction force, and because they act equal and opposite, again, momentum's got to be conserved. So two colliding objects, and this is where we're going to start to look at collisions and explosions. Two colliding objects experience equal and opposite forces for the same amount of time. And if we said that the impulse is the change in momentum, or the impulse is equal times the force acting times the time, and if the forces are equal and opposite for the same amount of time, like, is it clear to us why the times have to be the same? Force was Newton's law, but are we cool with the time being the same as well? I mean, if you slap the person sitting next to you, your hand is in contact with their face as long as their face is in contact with your hand. Like, it's not like you can let the hand go by and still sometime later their face is still touched. Like, it doesn't work that way. You're in contact with the object as long as the object's in contact with you. So the time is going to be the same either way, and the force is equal and opposite. We've looked at that through Newton's third law. So because this is true, Newton's third law, and time is time, momentum must be conserved. It's going to get moved around, but it's going to be conserved. And so the law of conservation of momentum looks like this. In an isolated system, and you might ask yourself, you might not, but you might, how isolated are we talking about here? How isolated does the system have to be? And the answer to that is as small as is necessary so that momentum is still conserved. If you're looking at something and the momentum's not conserved, then your system is too small. Something needs to be included that isn't. But don't make your system bigger than it needs to be. And in an isolated system where you're just looking at the objects that are doing the colliding or the objects that are doing the exploding, in an isolated system, momentum is not created or destroyed just transferred. And the definition I'll give you here for an isolated system is that in an isolated system, oh wait, you guys don't like that green. no external forces act. You're isolating the system to just the interactions between whatever your objects are. And if momentum is conserved, well, what that means is that the sum of all of the momentums at the beginning, however many objects you had, if you add up all of their individual momentums, they have to equal the sum of all of the momentums at the end. If they don't, you have a problem. It means something's not being accounted for. And this is true for as many objects as you have. And so we're going to look at some simple examples. We're going to look at a bowling ball hitting a bowling pin. We're going to look at a pool ball hitting a singular ball. And we're going to blow up a pumpkin. We're going to blow up a pumpkin? Yeah, we're going to blow up a pumpkin. And we're going to look at all of the objects that are involved in that procedure. So when you set up the equation, it starts simple. These e's here, or I don't know, maybe they look like backwards 3's to you, whatever they look like to you, should be something you've seen in math before. That symbol means the sum. So we're adding all these things up. So we're going to have mass 1 V1 initial plus mass 2 V2 initial plus ... plus, for as many objects as you have, mass x Vx initial, and that we have to add them all up, and that's going to has to equal the mass of 2 times the velocity of 2, the mass of 1 times the velocity of 1 finally, plus the mass of 2 times the velocity of 2 finally, plus ... plus the mass of the xth one times the velocity of the xth one at the end. Did you ask if I could explain it? Yes, I will continue to explain it. Have I lost anybody with this notation here? Okay. Oh, I would love nothing more, Jack, than to do that for you. We have the object number comes first, so object 1, its initial momentum. Object 2, its initial momentum, plus as many objects as you have up to the last one, which I've called object x. The mass of that xth object times its velocity at the beginning. You sum all of those up, that is the total initial velocity of the system. And don't worry, this will make more sense once we actually do some examples. This sum must equal the first object's final mass times final velocity, plus the second object's mass times final velocity, plus as many objects as you have up to the xth, or the last object, its mass times its final velocity. This sum and this sum must be equal, and because of that, we got some really interesting things that we can find. We're looking at two different kinds of collisions, and then we're looking at explosions. We good? Can I zoom out? Okay. So, the first kind of collision that we're going to look at is what's called an elastic collision. And at this stage, an elastic collision is, we're going to define it as objects don't stick together. There is a second definition that I will give you for elastic collisions in the next chapter when we talk about energy. And I should also make a comment here, so I don't know if any of you are concerned about this. One of the things that we're going to talk about here when we talk about the law of conservation of energy is we're going to keep everything one-dimensional. At this stage, everything is going to be one-dimensional. It's going to be left or right, or it's going to be up and down, or like it's just one plane of motion. If you want 2 or 3D, you're going to have to wait. So we're going to blow up a pumpkin, but the pumpkin pieces are only going to go left and right, which if you've ever blown up a pumpkin, you know is not true. If you explode an object, they go in every direction in three-dimensional space. That math gets really hard real quick, so we're not going to do it. We're just going to start simple because there's enough interesting simple examples that we can look at. So elastic collisions, objects do not stick together. If I've got a 7.1 kilogram bowling ball and it's rolling to the right at 3.8 meters per second, that is enough information to have the initial momentum of something, right? Momentum is just mass times velocity. So this bowling ball has an initial momentum. That mass times that velocity is going to give you the initial velocity of the bowling pin. So we've got that object there. It collides with a stationary 0.4 kilogram bowling pin. So we can start this thing. When you're dealing with collisions, there's always a before and an after. And then right in the middle here, that's where your collision occurs. So let's draw this thing. We've got a bowling ball. Bowling ball has 3 holes. We've got a bowling pin. I'm not great at drawing bowling pins, but we'll try. Here's the bowling pin. It kind of looks more like a pawn. Bowling pin has red stripe. There's the bowling pin. It's not moving. The mass of this object is 7.1 kilograms. The velocity of the bowling ball is 3.8. The mass of the pin is 0.4 kilograms. And the velocity of the bowling pin is stationary, so the velocity is 0. They're going to collide. Have you ever been bowling? The whole point of the bowling is to throw the ball at the pin. So, after they collide, there's going to be a better bowling pin. After they collide, the bowling pin now has some velocity. The thing's moving backwards. And the ball has some velocity too. Ball doesn't stop. If you've ever been bowling, you know this. It doesn't look like the ball slows down, but it has to. For the pin to start moving, the ball has to slow down. So this is the scenario. We know we're told that after the collision, the ball is traveling at, so the mass of the bowling ball doesn't change. It's still 7.1 kilograms. The velocity of the ball is now 2.9 meters per second. It's still moving to the right. The mass of the bowling pin hasn't changed. It's 0.4 kilograms. And now we want to know how fast is that bowling pin moving. And so that's the scenario. When you set this thing up, this is the equation that we're going to start with. When you have a collision or an explosion, we start with momentum initials equal to momentum final. And so now we can say, okay, we've got 2 objects at the beginning, we've got 2 objects at the end. So M1 V1 initial plus M2 V2 initial has to equal M1 V1 finally plus M2 V2 finally. We've only got 2 objects, so this is what the equation is going to look like. We plug everything in. 7.1 times 3.8 plus 0.4 times 0, this guy's gone, is going to be equal to 7.1 times 2.9 plus 0.4 times V2 final. That's what we're looking for. We want to know how fast the bowling ball is moving. And so now this is just an exercise in algebra. That's a 7, not a question mark. To isolate for V2, what's the first thing we have to do onto the right-hand side of this equation? What does the algebra say we should do first? To find V2 final. Don't all volunteer at once. Riri, hey, you're punching things into your calculator. It means you can answer my question. Or you want to you're multiplying everything together? Sure, you can do that. You don't have to, but let's do it. The 7.1 times 3.8, let's multiply everything together. This is going to be 26.98 plus 0 is going to equal 7.2 times 2.9. We don't need to, but we can. This is going to be 20.59 plus 0.4 V2 final. Sure, we can clean it up a little bit. Now what? Algebra says, what do we do first or next? Yeah, this is positive and it's being added to this, so subtract it over. I'll be real clear about what's going on here so we don't screw this up. 26.98 minus 20.59 is going to equal 0.4 V2 final. How do I get V2 final now by itself? This minus this is 6.39 equals 0.4 V2 final. How do I get V2 final by itself? Sorry? Thank you. Divide by 0.4. It's being multiplied. So the opposite of multiplication is division. Divide by 0.4. And what we're going to get is the final velocity of the second object, the bowling pin, has to be 16 meters per second. It's positive. So that means, and everything along here we assumed was positive. So to the right needs to be our positive direction, which means our bowling pin at the end of this whole problem, after it gets schmucked by the bowling ball, is moving at 16 meters per second to the right. So the bowling ball slowed down a little bit, but the pin sped up a lot, which makes sense. The pin's a lot lighter. Hopefully this is consistent with your experience. Questions, comments, concerns about anything I've done here? Okay, then let's do another one. It's going to look similar. We've got a cue ball. What's a cue ball? Are we all aware of what a cue ball is? What's a, when you do what? What sport are you playing if you have a cue ball? You're playing pool or snooker or whatever you want to call it, depending on where you are in the world. You're playing pool. So the cue ball is the white ball. Just so we're really clear on what's happening here. The cue ball is traveling, and it's 250 grams or 0.25 kilograms, is traveling east along the table at 4.5 meters per second when it collides head on with the 0.25 kilogram 8 ball. The 8 ball is the black one, for those of you who haven't played a lot of pool. Somehow, the 8 ball was already traveling west at 5 meters per second, which means you're not playing pool, you're screwing around on the table. When my buddies and I were in middle school, or I didn't have middle school, but late elementary school, one of our buddies had a pool table. And rather than actually play pool, what we did was one person was on one end of the table, one person was on the other end of the table, and we would whip the balls. You had to grab the edge of the railing, and we would throw pool balls at the other person's hand and the back and forth across the table. And your goal was to take the ball that you had on this hand, on your side of the table, and chuck them at the other side, to try and hit their hand or to try and prevent the ball that they just threw from smacking your knuckles. It was a really stupid game, but we played this game. That's effectively what's happening here. You've got a white ball moving east or to the right at 4.5 meters per second, and then you've got the black ball coming in, going the other way at 5 meters per second. They are going to collide. It says after the collision, the cue ball is now traveling west at 2 meters per second. So what you've done is, actually, this is the black ball. So what you've done is you've actually sent the white ball going back the other way at 2 meters per second. And the question is, what is the final velocity of the 8 ball? What is the velocity of this thing now? Which way does your gut tell you this thing should be traveling in? If you have 2 equal-sized balls and you smack them into each other, and now one of them is going back the way it came, what would you expect this one to do? Well, now we have both options. Kale, you're suggesting if these are equal mass, they're coming at each other, they impact, and this one's going left, you expect this one to go to the right. If this one was a lot bigger, yeah, then Colden, this one could still be going the same way it was before. But if they're the same mass, that's unlikely. So we expect it to be going to the right. We don't know how fast, and we have to see if that's true. Let's see if what Kale's gut says is true. Because we've got 2 different directions happening in this problem, now we need to have we call direction positive. Which way do we want to call positive? Sorry? To the right? Okay, cool. We can call to the right positive. Seems reasonable. So now when we have the sum of the momentums at the beginning equaling the sum of the momentums at the end, we have to take into account which way the balls are traveling at the beginning and at the end, using either positive or negative. So we're going to have the mass of the first object times its initial velocity plus the mass of the second object times its initial velocity, and that's going to equal m1v1 final plus m2v2 final. And now we're going to plug everything in. We said to the right was positive, and the first object was moving to the right, so that's going to be 0.25 times 4.5 plus the 8 ball has the exact same mass, except it's moving to the left at 5. So this is going to be negative 5 meters per second. I don't have to put the units in there. That velocity has to go in as negative because it's in the opposite direction of the first one. That's going to equal 0.25 times negative 2, because now the white ball at the end is moving back to the left. Plus 0.25 times v2 final. Again, we're looking for the final velocity of the second object. For those of you who are not mathematically inclined, you might just want to punch all this into a calculator. 0.25 times 4.5, 0.25 times 5. You've got a bunch of decimal values here. But in this very specific example, what's cool? Dwayne, what can we do? I'm asking you because you actually answered this exact same question correctly last week. What's interesting about what we've got here? You can cancel what? Out of it. Yeah, we can divide out the 0.25 out of everything. Because the masses of both objects are identical, we can divide everything by 0.25. Cancel, 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 cancel. And we're going to get this, our equation is going to change. We're going to get 4.5 minus 5 is going to equal negative 2 plus V2 final. Because the masses are all the same, the math gets really kind of fun. Easy. To solve this thing for V2F, we're just going to add 2 over to the other side. So then the final velocity of the second object is going to equal 4.5 minus 5 plus 2. 1.5 meters per second. And this value is positive. And we said to the right was positive. So what that means is this black ball has a final velocity of 1.5 meters per second east, which is what Kale expected, which is what Kale's gut suggested was true, and Kale was right. Comments, questions, concerns about what we've just done? Okay. If there are no questions, flip the page. Another example. So those are elastic collisions, and elastic collisions occur when objects bounce off each other. We're going to look at inelastic collisions, and this is where objects stick. So we've got tons of examples of this. You could have someone tackling someone else is an example of two objects sticking together. You could have train cars collide. You could have a car crash where the cars are mangled together. All sorts of different kinds of scenarios where you have objects that stick together at the end. One of the examples I've got for you here is this one. We've got a 0.105 kilogram hockey puck moving at 48 meters per second is caught by a 75 kilogram goalie at rest. If the ice is completely frictionless, so the goalie, he's not digging in. This is not proper goaltending technique. He's not bracing himself or herself. They're just, skates are pointing forward. They catch the puck like they were a bat catcher. Theoretically, the goalie should slide backwards. Question is, how fast? At what velocity will the goalie slide on the ice after catching the puck? So here's the scenario that we've got. We've got a puck flying through the air and a goalie. He's got some pads on. Presumably he has a glove. It's a horrible looking glove. That's our scenario at the beginning. They will collide, and afterwards, this is what you've got. Somehow the goalie got bigger. But now the goalie has a puck in his hands. And presumably, they're moving. So, the puck has a mass, 0.105, and it's moving. The puck is moving to the right, according to my drawing, at 48 meters per second. The goalie has a mass of 75 kilos and is not moving to start. The velocity of this is what we're looking for. What's the mass of the object on the right-hand side? It's going to be the sum of the two objects. They've stuck together. Now you have to have a total mass. It's going to be the 75 plus the 0.105, which isn't a lot. Like, don't get me wrong, it's not a lot of mass being added. It's 100 grams. But it's there. So what's that going to do? So it's a collision. We've got a momentum at the beginning is equal to the sum of the momentums at the end, and you have to include every object. Well, we're going to have M1V1 initial plus M2V2 initial. We've got two objects to start, and at the end, we've only got one. So the way I like to write it is I say that the mass of the total object times the velocity of the total object final, because we've combined all of the objects together. So this is going to be 0.105 times 48 plus 0, because the goalie's not moving. That's going to equal their combined mass, 75.105, times V total final. To solve this thing for V total final, we're just going to divide both sides by 75.105. So we're going to have 0.105 times 48 divided by 75.105, and that's going to equal our total. What is that number? How fast are the puck and goalie going to slide backwards after the goalie makes the save, assuming the goalie hasn't braced himself or herself? What's the final velocity? Y'all got calculators, use them. It shouldn't take anybody this long to punch that number in. Thank you. 0.067 meters per second. What that means is the goalie's sliding backwards at like 7 centimeters per second. Not insignificant, but not very fast. Okay. I would like you guys to try this one. I'll walk around and help where needed. It's the same scenario, except instead of a puck and a goalie, you've got a 35-gram bullet and striking a stationary 5-kilogram wooden block. It is exactly the same scenario. You've got a stationary object catching a moving object, and they move off together at the end. Draw it out. Set up your momentum equation. Except the only difference is in this question, it wants to know what the original velocity of the bullet was before it impacted the block. The question is exactly the same as the one we just did, except you're looking for the initial velocity of the bullet instead of the final velocity of the punch. Yes. So point. We're not done yet. No, wait. I'll do one more example. Grams are small. If you multiply by 1,000, you have 35,000 grams. If you multiply by 1,000, that would be 35 grams, being 35,000 kilograms. So you're dividing. You want to do this small time. Call me over if you have questions. Yes, sir. Yes, the mass for momentum masses always need to be in kilograms. You don't have to work in isolation. Talk to the people at your table. When you have a final velocity, let me know. That's the velocity at which they're moving off together, yes. Yes. That is 350 grams. Mass is too big. Wait, do you have an answer for me? Yeah, no, you're halfway.
We don't know what velocity is.
Yeah, mass is going to be kilograms, guys.
Wait. What would it for here? For velocity, velocity. Oh, it's zero. Velocity to initial zero. So this should be all zero.
Masses need to be in kilograms.
Right side of the equal.
The bullet is not a 35-kilogram bullet. That's like an artillery shell.
And okay, now I got it. Total would be 350 rounds. I have it. Okay. That's right. Okay, let's see. Yeah.
What'd you get?
I got 1237.
Yes. Yes.
My brain's breaking in. Maybe I was at one. Yeah. Look, man. I'm gonna be the first person in the world to bully him. You just gotta whip your hand back to slowly take off the speed. So you can't even catch it back and burn. Boom. Of course I can. Boom. How many kilometers an hour is that?
Divided by 3.6. The value you're getting is huge. It's actually about.
That's 340 kilometers.
You have to divide by 3.6, yeah. That's actually about. It's going to be about 200 meters per second faster than the fastest conventional rifles.
I could catch that. That's insane, bro. That's insane.
Yes.
Okay,
but sorry, Kai. Your birdie is going to lose speed quicker than that bullet's going to lose speed.
Is that speed that it measured? Is that the initial? Is that giving the initial speed, not the final speed?
That is the speed at impact.
I thought that would be the speed of which it crosses over the net. That would be.
Oh, sorry, I'm talking about my question. I don't know what speed they're measuring. Okay, so you guys are looking for a value. A bunch of you have it now. This is the setup. Again, this is the key that a lot of people were forgetting, that conversion from grams to kilograms. The value you're looking for is you want the value of object 1 initially to be about 1,237 meters per second. That bullet is moving. Oh, no, Kai. No. You multiply by 3.6 to go from meters per second. You multiply. You multiply. So this is absurdly fast. Faster than any conventional weapon is going to shoot a bullet. Okay. Are there any questions? Is anyone hung up on this? Does anyone want me to explain this further? There is zero shame. Hands up now if you want to see me. You know what? I'll just show you. I'll show you all. And now it's in the video and I'll talk you through it. So you got the two objects, converted the mass into kilograms. This is the setup. The sum of the momentums initially have to equal the sum of the momentums finally. You got the mass of object 1 times the velocity of object 1 initially plus the mass of object 2 times the velocity of 2 initially, and that's going to equal their mass together, or the total mass times the velocity of them together, total. So the stationary object's going to have a momentum of 0 to start. So it's going to be 0.035 times V1 initial plus 0 is equal to 5.035 times 8.6. Multiply these two together, divide by that mass, and you get 1,237 meters per second. Okay, I've got one more for you. Real quick, you're going to miss the last example. Okay. I have two questions here, and I'm going to do one of them. I will leave the other one for you to do as part of your work. So we've looked at elastic collisions, we've looked at inelastic collisions. Now we're going to look at explosions. In elastic collisions, they bounce off each other. In inelastic, they stick. In an explosion, the fun thing about an explosion is at the beginning, nothing is moving. There was no momentum initially, and then the thing goes boom. And you've got a bunch of pieces that are moving off in a bunch of different directions. In these two examples, we're going to have two objects moving one in either direction, which isn't super accurate most of the time. But one of these examples is pretty good. The first example has a bullet being fired from a gun. The bullet weighs 0.05 kilograms, so it's a 50-gram bullet. It's being fired from a 5-kilogram gun. So this is a large bullet being fired from a large gun. If the velocity of the bullet is 275 meters per second, so slow, what is the recoil velocity of the gun? So something that people don't often think about is when you pull the trigger on a gun, the bullet goes forward. Yeah, that's true. But Newton's third law says that gun also feels a force. The gun comes back at you. And if you're not prepared for it, a whole bunch of things can happen. So if you're standing holding a rifle the way you're supposed to, you want to brace it on the inside of your shoulder, and you're going to feel the impact of the butt plate on your shoulder, depending on the kind of gun that you. So I have a whole host. I have 6 or 7 different rifles. One of mine has a metal butt plate. It's a British rifle from World War II, and it's a Lee Enfield 303 British metal butt plate. You pull the trigger on that, and the metal butt slams into your shoulder. I have a hunting rifle. The hunting rifle, I put a rubber stock on it, a rubber butt plate on it, so when it has some cushion when it hits me in the shoulder. I have a double barrel 12 gauge shotgun, and you can pull both triggers at once, and it blasts the whole thing forward. And the fun way to hold, if you're holding it like a ridiculous human being, and if you've seen the movie The Terminator, you're firing it from the hip just to feel like a badass. The first time I did this, and I pulled both triggers on the double barrel shotgun, I stayed still. The bullets went that way, and the gun went flying out of my hands backwards, because I was not prepared for the recoil on this firearm. If all you're doing is watching TV shows and movies, you don't see this. But if you actually get behind a gun and start pulling triggers, you're going to feel it very, very quickly. It's an uncomfortable experience, and it should be. It should cost you something to shoot a gun physically. So that's the first example. The second example is a firecracker sitting inside a pumpkin. You light the fire, you put the thing in, you grab the thing, and boom, pumpkin explodes. And in this particular example, it only splits into 2 chunks, which is not realistic. It splits into 2 chunks, and the 2 chunks only go left and right. We know this isn't accurate. Pumpkin's going to go a bunch of different directions in a bunch of different pieces. Which example do you want me to do? Hands up for bullet from gun. I will do one of these examples. 4, 5, 6 of you. Cool. Hands up for pumpkin exploding. 3 of you. 4 of you. Okay, cool. Bullet from gun, and you guys get through the pumpkin question on your own. So, we've got a gun. There's the barrel. There's the stock. There's the trigger. I don't know, maybe you have a scope on the thing. Here's my really bad drawing of a gun. And somewhere in there, I'm going to zoom this thing in because that's a small picture. Somewhere inside there is the firing chamber, and you've got a bullet waiting for life. You pull the trigger, and the gun, there's the thing, there's the scope. The gun is going to move backwards. And the bullet is going to move forwards. Question is, what is the recoil velocity of the gun? How fast is that gun moving backwards if the bullet leaves at 275 meters per second? This is a slow velocity. Your average bullet, and that's actually a really heavy bullet, well, maybe it's not actually, 50 grams? I have to do some number crunching. Your average gun has a muzzle velocity of about 800 meters per second. So 4 times faster than this question. But let's play with the numbers that we have. So in an explosion question, initially, you've got one object here that has a total combined mass of 5.05 kilograms. And the velocity of this thing is 0. If you're doing it right, the gun's not moving. Afterwards, you're going to have the mass of the first object, 5 kilograms, and we want to know what its final velocity is. And we have the mass of our second object is 0.05. The two objects have separated. And we want to know, and we know, object 2 final has a velocity of 275 meters per second. Because these things are going in opposite directions, let's call to the right positive. Keep the big values positive. I don't know. And I want to know how fast this gun is going backwards. So, sum of the momentum initial is going to equal the sum of the momentum final. For an explosion, the initial momentum is always 0. And that's going to equal m1 v1 final plus m2 v2 final. So 0 is going to equal m1 is 5 times v1 final plus m2 is 0.05 times 275. The masses were already in kilograms for us. And now to isolate for v1 final, there's 2 ways we could approach this. I could either subtract this whole thing over, or I could subtract this whole thing over. It doesn't matter. For the sake of keeping this final value positive, I'm going to subtract over this whole piece. I'm going to subtract it over there. And so we're going to get negative 0.05 times 275 equals 5 times v1 final. Now to get v1 final by itself, divide by 5, and we're going to get a v1 final value of negative 0.05 times 275 divided by 5. And I get a value of negative 2.75 meters per second. This value is negative, which is what we predicted it to be too, by the way, because we said to the right was positive, and when you pull the trigger on the gun should go backwards. And in this case, the final velocity of the gun is negative. The gun's going backwards. Questions about what I did there? At this point, the physics is, you should see it's repetitive. It's easy, relatively speaking. It's the algebra that's going to catch a lot of you guys. Okay. I'm going to let you do this example. The firecracker. We are going to, for this particular question, because of how the whole thing is sitting, we're going to ignore the mass of the firecracker. And for those of you who don't know how firecrackers work, they start there, and then when you light them, they explode. Now they're gone. We're going to ignore the mass of the firecracker, and we're going to assume it gets vaporized. So all you're dealing with is the pumpkin. I'd like you to try this one as part of your homework. You're looking for a final velocity, because that's what the question is asking you to find. What is the mass and velocity of the other piece? Ignore the mass of the firecracker. The final velocity that you're looking for is 25 meters per second east. That's what you're looking for. I want you to try this question. I want you to try these guys here, all of them. And that is the end of dynamics. You got about 10 minutes left in the block. And you will have a short block tomorrow because we have pep rally. Yeah, y'all are going to get peppy. Sorry? Here you go. That is your work on your market set giver.